So yeah, welcome back to my YouTube channel, and in today's video I'm going to be talking about the Laplace transform of cos kt as we have done in our former video, but in this way we are going to be doing it using the exponential function, which is kind of like an easier way if only you can remember the exponential function, that is cos kt is equals to e raised power I at plus e raised power minus I at over 2. And the idea, not a, the a is the constant k, you don't have that a is e raised power I kt plus e raised power minus I kt over 2. That is the k here, is the k over here. And what if you can be able to remember this formula over here, you would have an easier way of finding the value of the Laplace transform of cos kt if you are not really good at integration by parts. So this is like an easier way for you to do it. So now let's move on. First of all, we have this, we put it into its form. We have f of s, or Laplace transform of cos kt, is equal to the integral from infinity to 0. Now f of t is cos kt, and cos kt is this, so we have this as into brackets e raised power I kt plus e raised power minus I kt over 2 times e raised power minus st dt. So first of all, 2 is a constant, you can bring it outside, and then we expand the bracket. So we have it as 1 over 2, the integral of from infinity to 0 of e raised power I kt times e raised power minus st plus e raised power minus I kt times e raised power minus st. Then we have our dt. This is inside bracket. We have our dt. So from here we just put it together using indices and integrate directly. So we have f of s is equal to the integral from infinity to 0, where we have e raised power minus into bracket s minus I k, and we put our t outside. Now I don't need to go into much explanation on why I put it in this form. Like I could just easily put the minus into this bracket and we have ik minus s. But the reason why we are bringing our minus out here is because we are assuming that s is greater than k. In such s is greater than k, and also we have to do it in that way in order not to get an invalid answer like s infinity minus 1, we have infinity or something, so that we can be able to get a valid answer. So let's move on with that. Plus in the other way, e raised power minus open bracket s plus I k, yeah, s plus I k, and we have now put the bracket back dt. So when you do the integration of this, this will be, let's not forget our 1 over 2, which is over there. You do the integration of this, we have that 1 over 2 into big brackets. Now I have e raised power minus open bracket s minus I k close bracket t over minus s minus I k on this edge, and also here we have plus e raised power minus s plus I k into t over minus into bracket s plus I k, now from infinity to 0. So what we just need to do is impute our value of infinity and 0, and we'll get our answer. So we have this as 1 over 2 into bracket of, yeah, if we impute our infinity, let me put in a smaller bracket into it so that we can be able to segregate our answers. Let me put a smaller bracket into it so we can segregate our answers. So I have here, we have 1 over e raised power infinity. Now the reason why it's e raised power infinity, first of all, t is what we are imputing the infinity into, and the minus sign is what makes e come down here. So we have 1 over e raised power infinity times whatever we have there, which is minus into bracket s minus I k, and plus 1 over e raised power infinity times minus into bracket s plus I k. We close our first bracket, that is when putting infinity to this, and now we put 0 into the value of t. So we have here 1 over e raised power 0 times minus into brackets s minus I k. Yes, do it this way. Then we have plus 1 over e raised power 0 minus into brackets and times is multiplied by each other, times minus into brackets s plus I k. Then we close our small bracket and our big bracket. So when we input our value into this, first of all, we shouldn't be doing like this anymore. If my infinity is going to give us infinity and anything divided by infinity is equal to 0. So this here is going to be equal to 1 over 2 big bracket. We have 0. This one here is 0 plus 0 overall. And here we are going to have it as e raised power 0 is 1. So the 1 multiplies everything. We have it as 1 over minus into bracket s minus I k, and we have plus 1 over minus into bracket s plus I k. Close the bracket and the bigger bracket over there. So now if we use this minus to multiply everything, the minus is going to cancel the minus that we have down here. So we are going to eventually have this as 1 over 2 into 1 over s minus I k plus 1 over s plus I k. Now we should already see where this is leading us if we can be able to view it. So first of all, we find our LCM and we have it as 1 over 2 into big bracket. The LCM is s minus I k s plus I k. Then we have s plus I k minus into brackets. No, it's not a minus here. We have it as plus. The plus sign is minus I k. Then we close our bracket. So we expand our denominator here. We expand our denominator. We have 1 over 2. Our denominator is going to be equals to s square minus into bracket I k square. So we have into bracket I k square, and here we have I k and we have minus I k. They cancel each other, so we have only s. We have s plus s. We have it as 2s at the denominator over here. So we can see that the 2 here can multiply the 2 that is over here. So therefore, if we expand this, we get s over s square minus, now the I there is an imaginary function which is the square root of minus 1. So when we find for the square of the square root of minus 1, the square cancels the square root and we are leaving minus 1 over here. That is times minus 1 then times k square, which is eventually going to give us s over s square plus k square. So therefore, we are being able to prove the Laplace transform of cos kt using this exponential function. So we can go through this once more, and this is like a substitute for using integration by parts for people that are not good with integration by parts. If you are able to keep this in your head, you will be able to prove the Laplace transform of cos kt anywhere. And yeah, so just impute the values. We use indices to sort it out, and after that, we find for the integration, we impute the value of infinity as 0. After that, we look for our LCM. Using our LCM, this resembles difference of two squares, which we put here, and they cancel each other. We finish up our work, and that is how we got s over s squared plus k squared.